Hello everyone and welcome. Today for lesson 3.2 we're going to be just digging a little deeper into the chain rule, getting some more practice with it and working with it in a couple different ways. So to get started, please go ahead and do the two do now questions. Pause the video and try those first two questions using what derivative rules you need. All right, let's take a look. I see here we have f of x, which is sine of x squared minus secant of 2x. So if I need its derivative, I see it's separated by a minus sign, so let's just take each term individually. I see sine of x squared. I have an inside and an outside function, so this is going to be the chain rule. I always start with the outside and work my way in. So the derivative of sine is cosine, but I leave the inside. Then we multiply by the derivative of the inside times 2x. Minus, now I need, secant of 2x. That's another outside inside. It's a chain rule, so the derivative of secant is secant, but then we keep the inside. But the derivative of secant is secant times tangent. So I actually end up with the inside in two places. Remember the derivative rule for the derivative of secant of something is secant of that thing times tangent of that thing. So this 2x that's on the inside will actually live in both places, and then we'll multiply by the derivative of the inside. This first part is the derivative rule for just secant of blah. We have secant of blah times tangent of blah is that derivative times the derivative of the inside, which is 2. And there we go. We could clean that up if we want. Now for the second one, the derivative f prime of x. I have tangent of 2x plus 3. Looks like another outside inside. So the derivative of tangent is secant squared of, we keep the inside, 2x plus 3. Now we take the derivative of the inside, which would be times 2. Derivative of 2x is 2, derivative of 3 is 0, so it's just 2. Plus the derivative of 2x is just 2. And there we go. There's just a quick review of our chain rule. We'll take the derivative of the outside, keep the inside whenever we have these composite functions. But this chain rule can actually go even further. And some of this stuff I'm actually pulling from the homework problems if you did the homework problems, the optional homework problems from this year, which I would typically have students do for homework required. What if we want to find the derivative of y equals the sine squared of 3x minus 2? Well, this is a little different. Whenever we deal with these squared situations, as I mentioned in class, we really got to think about these trigs to a power as sine of 3x minus 2, sine of blah, that whole thing squared. So actually, when we think about this, we have multiple layers going on here. The outside thing, the thing that applies to everything, is the squared. Then inside of that is a sine. And inside of the sine is a 3x minus 2. So the outside layer is a Dorito squared, a blah squared, something squared. Inside of that, I have a sine of something. And inside of that sine, I have 3x minus 2. Now I can apply my chain rule in situations like this where we have multiple layers. You follow the same pattern though. We start with our outside, and we work our way to the inside. We start with the outside, whatever that is, and then work our way through the different layers to the inside. So let's take a look. For this specific function, our outside is the squared. So my derivative is going to look like this. I want to take the derivative of the whole thing squared, Dorito squared. So that'd be 2 times whatever's on the inside, sine of 3x minus 2. I'm using the power rule here. I bring down the 2, keep the Dorito, subtract 1 from the exponent, so it'll be 1. Now I can move to the next layer, so it'll be times the derivative of the next layer. So the derivative of sine is cosine, but I'm going to still keep the inside. So the derivative of sine, which is cosine, I kept the inside. Now I can multiply by the derivative of its inside layer, which would be 3. Notice I'm really only taking the derivative of one function or one kind of thing at a time, right? I'm taking the derivative of the squared first, leaving its inside, taking the derivative of the sine, leaving its inside, taking the derivative of its inside, and there we go. This can be, I understand, still a little confusing. So let's take a look at another example. All right, here we have the quantity 1 plus cosine squared of 7x, that whole thing squared. Whoa, we got a lot of things going on. We can rewrite this. What we really have is 1 plus cosine of 7x, that whole thing there, squared, because remember cosine squared is the same thing as cosine of all that squared. But then that whole thing is squared. So again, let's start on the outside and kind of work our way in layers here. What do I have going on here? I have as an outside layer something squared, parentheses squared. Now what's inside of the squared? I have 1 plus something squared. So I really have 1 plus Dorito squared inside of that outside squared. I have 1 plus blah squared. And we need to kind of not get too stuck with the trees here. We want to take a look at the forest. We have something squared, then we have 1 plus something squared. Inside of that squared, I have a cosine of 7x. That cosine of 7x lives inside that something squared. What's inside that cosine? It's a 7x. So I actually have 1, 2, 3, 4 layers I have to get through for my chain rule. So I'm actually going to end up with 4 things multiplied together. All right, let's start. I start with blah squared, I take its derivative. The derivative of squared, I bring down the 2, I leave the blah. So 1 plus cosine of 7x squared. And I would subtract 1 from the power, so it would just be 1. So there we go. I brought down the 2, keep the inside. I did the power rule for my most outside thing. Times, now I need the derivative of what's inside of that. So I need the derivative of 1 plus blah squared. So what's the derivative of 1? It's 0. So it'll go away. What's the derivative of blah squared? It is 2 blah. Keep the inside. Times. Now I move inside of that. I'm now at the cosine layer because I took, remember, this second term here is the derivative of 1 plus blah squared. I brought down the 2, left the blah. Times the derivative of cosine. Ooh, I think I lost a parentheses in there. I actually had an extra one. I guess I don't really need this parentheses there. All right, times the derivative of cosine is negative sine, but I'll keep the blah, keep its inside. Times, now I need the derivative of its inside, which is 7. Notice I'm taking one derivative at a time. I took the squared derivative, but left the whole inside. Then took the derivative of that inside, but left the cosine in the 7x. Now I took the derivative of the cosine, left the 7x, times the derivative of 7x, which is 7. And we can actually do this for as many layers as we want. If you want a good test, have me write you a kind of crazy looking chain rule problem with like 7 or 8 layers and see if you can do it. All right. Cool. I'm going to do one more here for you, and then we're going to kind of alternate practicing some. All right. dy dx in this case. I see we have a cubed, and remember in these things, these powers are outside of the sign. So we have a cubed, a sine, and then a 4x. So my derivative of something cubed will be 3 something squared, but I'll keep all that inside stuff. The sign doesn't change. The 4x doesn't change. We're just taking the derivative of the power rule thing. Times, now I can move to inside of the power, which is sine. The derivative of sine is cosine, but I leave the 4x. Times the derivative of the 4x, which is 4. Again, the outside layer, if we want to label it, if it helps, is Dorito cubed. Inside layer 1 is the sine of Dorito. And then inside of that, the inside layer 2 for this guy was the 4x. All right. Go ahead and try 12 here. If it helps, label out what are your outside, inside, inside 2, inside 3, or so on and so forth for this, and find the derivative. Pause the video and try that. All right, let's take a look. We have tangent of a bunch of stuff. So tangent is definitely our outside. The derivative of tangent is secant squared of, we just leave everything on the inside. All right, so now let's look at the inside. We have 1 plus cosine of 3x squared. That squared is outside of everything, so I have 1 plus Dorito squared. So let me take the derivative of 1 plus Dorito squared. Derivative of 1 is 0. The derivative of something squared will be 2 something. And we'll leave the inside parts. Okay, we just took care of the 1 plus blah squared and got 2 blah. Now what's the next layer? Cosine is our next layer. So I'm going to say times, I'm going to move to another line, sorry. The derivative of cosine is negative sine. I want to keep the inside part there. Now I move inside of the cosine, the thing on the inside. Cosine was 3x, so I'm going to multiply by 3. All right, cool. There we go. We have the derivative now. It was 1, 2, 3, 4 levels here in this chain. Keep in mind, we're only going to do one derivative at a time. We did the derivative of secant, then we did the derivative of 1 plus blah squared, then we did the derivative of the cosine, and then we did the derivative of the 3x. All right, go ahead and pause the video and give these a shot. They get a little more challenging and flex some of your different derivative rules. Give it a shot. Try 13 and 14. Pause the video and try that. All right, here we go. Remember, it helps rewrite stuff so you can see the different layers. This would be sine of 2 to the 3x plus 1, that whole thing squared. So g prime of x, I'm going to start with that squared. It'll be 2 sine of 2 to the 3x minus 1. Now next inside is the sine. The derivative of sine is cosine, and then 2 to the 3x minus 1. And the derivative of sine is cosine, but then we kept the inside. Now I need to take the derivative of the inside of that. So the derivative of the inside of that I have 2 to the 3x minus 1. Oh my gosh, that's another chain rule. The derivative of 2 to the blah is natural log of 2. Keep the 2 to the blah. Right? Because the derivative of 2 to the something is natural log of the base times the exponential thing. Now I need to multiply by the derivative of its inside. In these exponential things, the inside is always the exponent part. So the derivative of 3x minus 1 is 3. This was 1, 2, 3, 4 layers. All right. Change color here to make this a little more clear since running out of space there. All right, derivative of kx. So I need k prime of x. On my outside layer is natural log of Dorito. So the derivative of natural log is 1 over the inside, 3x plus sine of 2x. Okay, then I would multiply by the derivative of the inside. The derivative of 3x is just 3 plus, now I need the derivative of sine of 2x, but that's a chain rule. Wow, so we actually have something kind of complicated going on here. We have natural log of Dorito, we took that derivative 1 over Dorito, times the derivative of 3x is 3, because we're taking the derivative of the inside part here, 3, plus the derivative of sine is now a chain rule. So the derivative of sine of 2x is cosine of 2x times 2. Interesting. And number 14 here actually leads us to some interesting thoughts, that sometimes these rules aren't just applied in a very straightforward way. We have to be really flexible. So what I encourage people to do is first, when you get to these more complicated derivatives, look at what we call the superstructure. What is the overall kind of controlling structure of the function? Is it like mostly a composite function with something inside of something else? Or is it mostly a product? Is it mostly a quotient? Look at the superstructure. Then determine that superstructure. Is it a composite? Is it a product? Is it a quotient? And then determine the substructure. What is then the next sort of layer of things? Within the product, do we have a chain? Within the chain, do we have a product? Let me show you what I kind of mean by that. Here's an interesting example, also from the homework from 3.1. Y equals the sine cubed of x times the tangent of 4x. I notice here that our superstructure is a product. How do I know that? Well, if I kind of break this down into something really simple, what I really have here is the y times some function, y equals some function, that function happens to be sine cubed, times some other function. Those individual functions are kind of complex, yes, but in general, I have something times something else. So my superstructure is a product. But look, each of those f of x and g of x, the substructure is a chain rule. I will need my chain rule as I do my product rule. So let's do that. dy dx. I notice my superstructure here is something times something else. So I start following the product rule. The product rule says keep the first times the derivative of the second. But like we said, the substructure is a chain rule, so the derivative of tangent is a chain rule. Secant squared, I take the derivative of the outside, keep the inside, times the derivative of the inside. So my superstructure, I'm doing that to derivative rule first, because that's my controlling derivative, product rule. Keep the first, derivative of the second. The derivative of the second just happens to be a chain rule. Plus, Now I switch for my product rule. Remember, my superstructure is my product, so I'm going to keep doing my product rule. Now I take the derivative of the first, but the derivative of the first is a chain rule. So 3 sine squared, of x times the derivative of the inside. The derivative of the inside of the power is derivative of sine, which is cosine of x. So I took the derivative of my first function, that's my substructure, it's a chain rule, times keep the second. And I know that can be confusing. If you need to, replay that section I just did, but I recognize that the product rule controls the whole thing. I have f of x times g of x. I follow my product rule, but when I need to apply the chain rule, I do. I keep the first, derivative of the second is a chain rule, plus derivative of the first is also a chain rule, times keep the second. All right, here's another one. Ooh, interesting. So let's see what we have here. Sometimes it helps to rewrite stuff. What do we have here? We have the square root of something. In fact, if we want to rewrite this, we have let's call theta f of x. We have g of x, which is sine of theta, and that whole thing raised to a half power. So what's my superstructure here? My superstructure looks like a composite function, something inside of something else. So actually my superstructure is a chain rule. But inside of my chain rule, I got a product. My substructure is a product. Let's do that derivative. All right. So since my superstructure is a chain rule, I start my chain rule. My chain rule says keep the inside, but take the derivative of the outside. So the derivative of the outside would be half. I keep the inside, so that's going to be theta sine of theta. Take the outside, which is derivative to the half. So I brought down the half, keep the inside, subtract 1 from the exponent, times the derivative of the inside. But the substructure of the inside, the next step is going to be a product. I have something times something else. So my product rule, I'm going to put this in parentheses, the derivative of my inside is a product rule. I keep the first, derivative of sine is cosine. Keep the first, derivative of the second, derivative of sine is cosine, plus derivative of the first, derivative of theta, is 1, times keep the second. And again, this is a product rule. It's the product rule of the inside part here. Because I have derivative to the half. It's a chain rule, so I did the derivative of the outside, kept the inside. Now I need the derivative of the inside, which is a product rule. Keep the first, derivative of the second, plus derivative of the first, keep the second. I realize this over here should be dy d theta, since we're not, our variable here is a theta. That is a wonky looking theta. All right, let's change that. Like an X-Men logo or something like that. dy d theta. That still didn't look great, but we will survive. All right. Cool. I want you to get some practice with this. We're going to work through some challenging sort of things here. Go ahead and pause the video. Try problems 1 and 2. And then come back and check your work. All right, let's take a look. Determine the value of g prime of 1 if g of x is this thing here. All right, so we look at our overall structure. It looks like we have a product, something times something, but in that product we also have a chain. All right, g prime of x then. My superstructure is my product rule, so I keep the first times the derivative of the second, but the derivative of the second is going to be a chain rule. So I have derivative cubed, so I bring down the cubed, keep the inside, subtract 1 from the exponent, times the derivative of the inside, because I'm in the chain rule land for the derivative of the second. So that's going to be times -4, plus, because I did keep the first, derivative of the second, but the derivative of the second was a chain rule. Now I take the derivative of the first, which the derivative of sine is cosine, times keep the second. All right, we want to find g prime of 1. So all we would have to do is plug in stuff. This we actually can't simplify very much because the sign of 1 is not something that we sort of know off the top of our heads. So I'm just going to plug in, not do much simplifying. That'd be 3. If I plug in 1 here, I'm going to be 3 minus 4, so that'd be -1 squared times -4 plus the cosine of 1 times 3 minus 4, which is -1 cubed. All right. Determine g prime of x if g of x is this thing. Woo. Wow. Okay, well, I have something cubed. So my superstructure looks like it's a chain rule, something cubed. I have something cubed. But that something, the inside, is a quotient. So we got to be on the lookout for that. We're going to start with our chain rule, but then we're going to end up doing a quotient rule in here somewhere. All right, g prime of x. I have blah cubed. So the derivative of blah cubed is bring down the cubed, keep the inside. Ooh, this is going to get a little crammed. Sorry about that, y'all. Bring down the 3, keep the inside. We subtract 1 from the exponent. Now I need to take the derivative of the inside. I start my chain. I have Dorito cubed, so I took the derivative of the cubed, kept the inside. But now look, the derivative of the inside is a quotient rule. I'll put the quotient rule in a different color. Let's say blue. All right. So my quotient rule would say, actually, if it helps, we could put big brackets around the quotient rule. My quotient rule will say low. So I keep that whole low function, 3x squared minus 2 sine of x. Put that all in parentheses. Low times the derivative of the high. Derivative of e to the x is e to the x. Low d high minus the high function times the derivative of the low function. So the derivative of 3x squared is going to be 6x minus 2 derivative sine is cosine of x. So that's the derivative of the low function. So I did low d high minus high times the derivative of the low all over the low function, 3x squared minus 2 sine of x squared. Wow, that's a crazy looking derivative. We did the chain rule, kept the inside, but the derivative of the inside is a monstrous looking quotient rule there. Woo! Not sure where that woo came from. All right. Cool, I know that can be a little complicated. Take a minute to sort of digest that. All right, we're going to do just a few more, not all of these, but I will recommend that you do some of them sort of on your own if you want a good set of practice, okay? Let's say we have this function. We want to find all the values for which g of x has horizontal tangent lines. Now remember, what does a horizontal tangent line mean for our derivatives? Well, horizontal tangent lines are going to be where the derivative is 0, because if a tangent line is horizontal, it is flat, and the slope of a flat or constant line is 0. All right, so first we got to find the derivative then. The derivative looks like we need the chain rule. We got Dorito cubed, so the derivative will be 3, keep the inside. Subtract 1 from the exponent, times the derivative of the inside, which would be times negative 4. That's a times there. Okay, cool. All right, so we did the derivative of the outside, kept the inside, times the derivative of the inside. Sweet. Now we need to make sure we want to figure out where this is equal to 0. So we go, okay, well, where's this going to be equal to 0? Well, really, this is negative 12, 3 minus 4x squared. Sorry, ooh, I put the squared in the wrong place. That's odd. 3 minus 4x quantity squared equals 0. So where's this going to be 0? It's going to be 0 where 3 minus 4x squared equals 0, because I can divide negative 12 to both sides. I can take the square root if I want to. Right? Well, that's just going to lead us to the fact that wherever 3 minus 4x is 0 is going to make this, the squared of that 0. So we solve this equation, and we'll get x has to be 3/4. There we go. When x is 3/4, the derivative will be 0. Let's see. We want to find, here's g of x. Let's find the second derivative. Remember, for those things, all we need to do is take the derivative multiple times. So take the first derivative, g prime of x, would be, we got what looks like a product here, but then part of the product is a chain again. Okay, so I'd keep the first times the derivative of the second, but the derivative of the second is a chain. So I bring down the 3, keep the inside, squared times negative 4. We've seen that derivative already. Keep the first derivative of the second, plus derivative of the first, which is just e to the x, keep the second. Well, this is interesting because this second part is actually just our original function. So when we go to go, actually, let's clean this up a little bit. E to the x, right? E to the x times 3 times negative 4. Let's call that negative 12, because 3 times negative 4, negative 12 e to the x. 3 minus 4x squared plus e to the x, 3 minus 4x cubed. All right, so this part over here, right, is actually what we started off with. This part is new. So when we go to do our second derivative now, we can actually save some time. Our second derivative, I look at my first part here. Uh-oh, looks like I got another product rule with a chain. So I can do that part. The product rule says keep the first, negative 12 e to the x, over constant multiple stay, the derivative e to the x, or just keep the first, negative 12 e to the x, times the derivative of the second, which in this first product right here is 3 minus 4x squared. So that's a chain rule. Bring down the squared, keep the inside to the first power, times the derivative of the inside. So I kept the first times the derivative of the second, which was a chain rule, plus derivative of the first, so derivative of negative 12, that would be a constant multiple, so it'll stay negative 12. Derivative of e to the x is just e to the x, and we keep the second, 3 minus 4x squared, plus, look, now we need to plus this derivative, which is a product rule. It's actually the product rule we already did. So I actually just need to copy down, if this is the derivative we already did, I just need to copy down this whole thing again, because this whole thing is actually going to be the derivative of this one. So I'm just going to copy down negative 12 e to the x, 3 minus 4x squared, plus e to the x, 3 minus 4x cubed. That's a long set of derivatives, but it works. Again, this last part here I shortcutted because this last part comes from the derivative of this, which I've actually already done. That was my original derivative. All right, let's take a look at one more. Actually, yeah, so I want to leave 5 and 6. Those are good ones. I would like you to try, if you have time, good practice. I'll look at 7 real quick and then let you know what your final assignment is. We want to find h prime of 4, given that h of x is defined as f of g of x, and following the value, given the following values here of f of x and g of x. So if we want h prime of 4, and I know that h of x is f of g of x. Well, if I want the derivative of this, what is my derivative rule? What structure do I have? Well, I have an inside and an outside function, so this is going to be a chain rule. Chain rule says take the derivative of the outside, and whenever we're given things in function notation, let's leave it in function notation. The derivative of the outside is f prime. We keep the inside times the derivative of whatever that inside function is. So there's actually our derivative of, that is, h prime of x. We do this especially for free response questions on the AP exam because they often will score this. Then we can plug in our value. H prime of 4 is going to be f prime of g of 4 times g prime of 4. See if you can use the table to figure out this value now. All right, so h prime of 4. G of 4, what is g of 4? G of 4 is negative 2. So if g of 4 is negative 2, that leaves us with f prime. G of 4 was negative 2, so that's f prime of negative 2 times g prime of 4. G prime of 4 was 2. So what is f prime of negative 2? F prime of negative 2 was 3 times 2. My final answer here is 6. So follow your derivative rules as you know them, leave it in function notation, and then use your table to evaluate, starting evaluating on the inside and sort of working our way out until we have our final answer. All right, if you have time, go back, try 5 and 6. They're good questions, and you can have me check if you would like. For the remainder of your time for this lesson, I want you to do another round of D&D chain rule. This one's a little different. The instructions will be on the Nearpod, but you're going to essentially do the same thing. We're going to, this time, battle a monster and keep track of the monsters up here in your grid. Copy down each problem, battle the monsters, find the loot, and then let the loot lead you to the next monster to battle. You're going to keep track of the order of monsters as the loot leads you to each monster. You might need to simplify or re-express your loot to find what the next monster is. Further instructions will be in the Nearpod. Try that. You'll do all that work and then upload your work to the assignment on Google Classroom. Optional homework is worked in here. Please, if you have time, do great questions. The chain rule comes up so often. Also, in here I accidentally forgot to erase this. Ignore the in Taylor form part of this. Ignore the in Taylor form part of this. But here are the worksheets. Definitely worth a try if you get a chance. Please, please, please see if you can try those. All right? Cool. Good luck, and let me know if you have any issues, and I'll see you next time for 3.3.